Good afternoon. My boss was supposed to do this talk, Justin Ratner, and he would have definitely done a very different talk. And I first thought about just doing a pitch that he would have done, but that would have been just artificial. And you would certainly not see an Intel presentation without Moore's law, without billions, millions, powers, transistors. And I thought about it and decided to take a gamble. So this is a different talk, a talk that I can do more naturally based on my IBM research experience and here at Intel. And this is not a single graph or plot or a number or millions, picojoules, anything. So it's definitely yet another attempt at different talk. So first of all, who we are PAL Computing Lab. And to complement what rest of the Intel, or rather rest of the industry does, we don't go bottom up, we come top down, right? And of course, it's a matter of iterating. So we do vertical stuff, which we hope rest of the industry doesn't do. So when we're working with a company, whoever, right, Google's, Apple's, or Wall Street's of the world, our mindset is very different. It's as if we're building a system just for that one guy or that one application. It's that mindset is how we do this research. And in the process, we discover or we figure out what's the most optimal system design point is. And if that's too far off from what we are building, something will happen. And therefore, we'll have to address it. And that's exactly what has happened. The big outcome of this research is a new processor roadmap that you probably have heard of, something called Mike, which directly came out of this research. So I'll refer to that in the second half of my talk. So like I said, we start from the top. We work with just handful academics and industry players. We only pick an area if we find an industry co-traveler as well as an academic co-traveler. It's between the two of them that somehow the equation, somehow everything completes. And we are incomplete if we only found one of them. So and then we get going, and the primary focus area at this point, I just briefly listed where we have been focusing on architecturally and workload-wise. And then try to go into more details. Architecturally, our biggest problem that we are facing at this point, we are past that point in our first generation of this research. In my previous first 4 or 5 years of this research at Intel, we are mostly talking about needing more cores. And I joined Intel 2003, and we are still talking about single core machines, Itanium ruling the world, and such things. There was no multi-core mindset. Right, and somewhere there, as I think 2004 or Ottolini talk or whenever this happened, and now we're at a point where we already passed the point of number of cores or flops. There are only too many flops rather. The real challenge has shifted from compute to data. So the primary architectural focus is feeding the beast, right? How do you really feed data to where the compute is? And compute is least of the problems in many ways. And the other challenge is that it's very difficult to come up with solutions that work in general. So we are really focused on domain-specific solution, graphics being a good example of how problems have been tackled and become simpler when you focus on a domain. I mean, I did a lot of my time at IBM was spent during speech recognition. Same thing, a problem in general may be hard. You focus on a domain, and now good enough speech recognition systems are sold to radiologists or in cars. So the focus and narrow the domain, and you can offer and you can see significant acceleration opportunities. Finally, we are looking at not the 2-4 thread machines or 100 core machines. Those are there. But the way you go from 1 core to 2 core or 1 thread to 2 thread or 10 thread is very different than how you go from 10 to 100,000. So we are looking at how do we build massively multi-thread machines. And the last two are also very important topics. So somehow, anyway, unstructured accesses. Most of our focus is on unstructured accesses because most of the problems now are irregular data problems. So the regular problems are relatively easy, and most of the world out there is not relational databases but unstructured blocks. So our primary focus architecturally and research-wise is really on understanding irregular large data sets, irregular problems, unstructured accesses. In one word, the workload is simply massive, large data set, multidimensional data set, and you have to index it, right? So finally, the interesting part of the talk, interesting part of our research is distributed decomposition, because distributed decomposition hasn't so far has always been around, but it's becoming a much more of a requirement, and I'll offer some of the motivations. So most of the time we no more are struggling trying to break the problem into few cores and integrated CPU, GPU on die. We're doing that, but the real challenge, the real ROI, the real return on investment happens when we can actually decompose the problem over the cloud, and that's where the real efficiency and return happens, when you can truly decompose it. And that also ties into how you can make use of computing that's not necessarily concentrated, right? Workload focus wise, I already mentioned, we do a lot of, our primary focus is more on the commercial side of HPC. So we do a lot of Wall Street, a lot of Hollywood, a lot of medical and seismic. They just happen to be 4 parts of the US. We work very closely with Mayo, so they happen to be 4 geos of US. We're now also doing significant amount of database in memory analytics work. So massive data computing, and we just started this year non-numeric computing, large graph problems. In fact, we just submitted this week a large graph problem paper. And primary learning, if I had to summarize it in one word or one sentence, at least it may be a biased view, but I think a huge inefficiency lies in how algorithmically, there's a huge disconnect in how machine resources are used. So there's a big impedance mismatch in people's traditional thinking, and less in the case of HPC guys, but more in the commercial world out there. Traditional thinking on how algorithmically people have been approaching problems, it's very anti-parallel, the mass solutions that are out there. And thanks or no thanks to the kind of machines we've been building, largely single core machines, out of order, whatever. So that impedance mismatch is responsible for most of the efficiency loss, and the return you get there. It's like my advisor used to say, Mike Flynn, that time lost is lost forever. That algorithmic disconnect is a huge source of inefficiency. And just to give you one data point, we have achieved on this paper, on a single socket Nehalem graph problem, which is listed in top 500 with 256 nodes. So the 256x disconnect is because you need to sit down and really understand that algorithm in system-friendly terms. And the algorithms that are out there are really unfriendly in terms of the multi-core or the architectural trends that have happened. SIMD, caches, go on and on, the 3 or 4. So most of our papers we're trying to understand how to bridge that gap. What's the new abstraction that can really bridge the gap and deliver efficiency? We got Best Paper Award at SIGMOD last year, same thing, right? It's for large tree search, graph search problem, huge inefficiency, not 10x, 2x. More than that lies in not being able to match the system trends with the algorithmic nature. So I was part of a National Academy task force which just concluded on sustaining growth in compute performance. And these observations somewhat come from there. And in interest of time, I'll just focus on the new or recent catalysts for compute. I mean, traditional catalysts for compute, I'm sure at least people here are very well familiar with. But I'll just emphasize what's recently happened is very important, and it's important to understand what's new, what's now driving compute. And the first one is more, at least to Intel, to us, very important, which is changing demographics of computer users. Most computer users used to be people like me and you, were designing yet another machine, and for geeks and nerds. But the primary growth in industry is coming from a very different demographics of people. They could be farmers, they could be in emerging countries, and that's the people who, and those guys, the way they use compute and what they're looking for, the requirements are very, very different. People roaming around with phones or waving their hands. So you need to understand what it means to address their compute need. And compute requirements for them is not necessarily simple or cheap. It's multi-exaflop also. It's just a matter of understanding what the grandma wants. Right? And video karaoke is not a simple application, it's a very expensive application, right? And who doesn't want? Of course, kids are jumping up and down with audio karaoke. Video karaoke would be even better hit. They wouldn't be jumping on a mat at Fry's. Now, but doing that is extremely difficult. So it's not a matter of end user not needing it, but how do you meet an end user need which has a very different user interface? He'll not sit and code Java or SQL is an important consideration. Then the second one is this is a point we are in. We are at a point where massive data is finally meeting massive compute. And massive data that's not just accessible to a government agency or some secret service, but accessible to all of us. That YouTube impact, that kind of Picasa impact on how you approach traditional problems is very, very important. So often we are able to now find massive data approaches to the traditional problems, and these are a lot more power friendly and a lot more, not better approaches, and algorithmically efficiency wise, and they've been known for some time, but the data just wasn't there, so you resorted to heuristics which rarely worked. So the last one being connected computing, the fact that it used to be very difficult to find a machine which was connected, and now it's the other way around. So how do you take advantage of these three trends? And in my view, these last three trends on who the real computer users are, the guys holding iPhones or not even holding iPhones but sensors embedded, and villagers, and the convergence of massive data with massive compute, I think first time in the history of computing, finally, fact that it's all connected has huge implications on how we've traditionally viewed problems and how we can derive efficiency. So we've been spending a lot of time in understanding and modeling such problems, right? What is at the crux of it? How do we really model such applications which can be like all those Hollywood to Wall Street type applications? And this is, you can probably find reference to this in our IEEE proceedings paper. We explain how our workload view, but this is our view of understanding or modeling these. And all these applications at very high level, you're basically asking the simple three questions only, right? What is it? And that's really at the crux of computer trying to understand what is that you're after. You could be the object or event that the computer is trying to model, that the user has in mind. It could be a flower, it could be a terrorist, it could be stock trading opportunity. Some event or object is the what part of it, right? And huge amount of cycles go in just modeling that object. And if you have a good model of that object, you'll have a good output. But the goodness of the model at the end user level is only judged one of two ways. The output of the mining, like can you find me similar things? Can you find me flowers like this? And go Google it. Go back in the past and find something similar. If you're good at finding what I'm looking for, you must know what I mean. Or synthesize, simulate in the future. If there is no such a flower or Madonna that exists, create such a one, create some such. So synthesis or mining are the only two ways an end user, a grandma or grandpa, really judges the goodness of the model that computer has. Now, what the power of massive data is that these models can now be refined real time, continuously, as opposed to just hoping and praying for a good model. And that's why you have to be able to iterate. And for most problems, we're not as lucky as the typical Navier-Stokes type, where you have a deep understanding of the problem. We have almost no understanding of the problem, especially behavioral problems. So in all these cases, massive data comes to rescue. We may not know the causality. We never be able to write that equation, but we can still track those problems. The problems become tractable because of huge amount of data. That massive data approach, and there are several examples of this, including the medical world for a huge amount of functional MRI data to figure out what the guy is thinking. Such bizarre examples to much more close to our usages where we can replace large matrices by just computing. So the centerpiece here is really the one that runs on the server side, because that's where the massive data will reside. Your laptop will never have enough data. But huge amount of data, hundreds of millions of images, will only be residing on the server side. So that inner loop is where that large amount of data is constantly created, an ontology is created and structured-fied, XMLized. And the outer loop is where the end user sits. So the end user, like it could be me or you or whoever is blogging or trading, that end user loop is generally a visual computing loop. Some image or some model to back to the computer and then model back to the image. Right? That's how you interact with the 3D world. So that outer loop is a visual computing loop, graphics and vision, and the inner loop is where the most of the compute and the server-side compute happens. Now, the power of all this is that we are now able to do the amount of compute that we need when you're able to reiterate real time. The best example of this is Wall Street, where trades happen in milliseconds, not because someone is hitting a keystroke. That's too slow, right? Professor Norman analyzes a gap between how long you think. Because the trade happen, all program trade, you can actually go in milliseconds, and then once in a while, after some seconds, you are told whether your bot found something or succeeded or not. So the end user, human user, is still in the loop, But the machines now, the inner loop can go a whole lot faster than the human response time. So it's not even limited by how fast I can hit a keystroke, how many colors I can see. The inner loop can actually go a whole lot faster than the outer loop. So this is why this drives the insatiable need for compute when you have huge amount of data, because and it's being enabled because of the software infrastructure that's happening, XML and then some ontology language. So that URL to XML to some a basic RDF is what's driving this semantic web-like thinking, right? And that's really so the simple, our view of computing therefore is that the very outer loop you have humans or someone, and that loop is largely driven by sensing of some kind. It's currently driven by output. So your computers used to have, you type a few keystrokes and you see a few keystrokes, old machines. Something happened and now you type only few keystrokes, but you get to see 3D view or 3D world. So it's been too much output dominated. It's only a matter of time with the cameras becoming so cheap, sensing, the input side will dominate again. Anyway, the input side, the sensor, camera or output visuals, where you have to go through a transform from whatever that FFT-like domain back to the flower building or color or user domain is very expensive task, but that's what will dominate the outer loop. Okay, and the inner loop will be massive data analytics. That's where the huge amount of data would only reside in some cloud, and that's the only time you can actually model the world with that amount of data, not with one user's data. So if that being our worldview of emerging applications and the compute model, it becomes the key driver where I want to spend just a few more minutes on is really this opportunity of massive data computing. This massive data computing has big implications on how we build computer, how we efficiently use them, and it's not simply a matter of going from LinPack to Graph 500, which you're already seeing in HPC world. It's a whole lot more than that in terms of its implications, right? And like I said, the whole data-driven models are basically letting us track or address problems which so far were unaddressable because no scientist gave us that nice equation formulation, some PDE to solve. A whole bunch of problems now become tractable, even though we may never have that closed form or analytical understanding just because we have large amount of data. And the connectivity is a big boost here. That internet has almost in quality reliability you'll call a burn-in effect. It speeds up things big time. As opposed to me trying to train the system on what I talk, how I look, that instead of tossing a coin million times, the coin gets tossed, million coins get tossed in a second. So the learning happens amazingly fast on the web. And Google may have no notion of who some Indian politician is, but if that guy is popular, 5 seconds later, Google knows all about it. Not because I'm constantly asking a question, whole number of, all kinds of people are asking right away. So that learning, that connectivity, and that real-time training where you can start with a very poor model, but you quickly improve it, is at the heart of this massive data computing. So now I'll spend a while where I think the most relevant from the point of view of audience here is our, at least application-centric view of where the energy efficiency opportunity lies. Clearly it's a biased view, but we believe that there's a huge opportunity in really re-understanding or recasting or understanding these problems from the emerging applications and realizing how to map them most efficiently on the multi-core, many-core trend. Because if you don't think, the two are very, very different. Take, for example, a large graph problem. If you simply take a problem and map it, almost every node, every vertex will be a page walk and be huge and efficient. And you conclude that I need megawatts for building or for doing these connectivity social network problems. Reality is there's a huge inefficiency in how that problem gets computed today. Because of the algorithms, the machines, the locality, the core friendliness, thread friendliness, cache friendliness, SIMD friendliness, none of that stuff exists. And the parallelism is really infinite of what kind? Of data kind. It's a huge amount of data that's at the heart of parallelism here. So you have to be very, very efficient in dealing with data parallelism and unstructured, irregular data parallelism. Because a huge amount of parallelism lies along a dimension where you may not have seen. So that's where the whole opportunity lies. So the first part is also realizing that most of these emerging applications are not like calculating the balance in a bank statement. These are all statistical problems. There is no good output. There's no perfect search output. It's just more compute. So there's a nature to it, statistical nature to these problems, and that's what makes it very attractive, very appealing to match that statistical nature of the problem with the nature of the system we build. which will be increasingly failing all the time for all kinds of sub-nano reasons as well as how data center reasons. But you deal with them at a software level and algorithmic level, that's a more efficient place to deal with them as opposed to at the very lowest level. And locality awareness, data and compute, the examples of these few papers we have recently published, everywhere it's a 10x, 100x type efficiency gap lies in not being able to understand the core and compute density and what's growing and what's not growing. Bandwidth is not growing. So you have to be really understanding of the locality aware programming and locality of a working set of your problems. Working set used to be only a matter of cache megabytes, and people never worried about working set after that. You need to understand the working set at a higher level of the kind of near memory systems and flashes and embedded RAMs that we can now build. And then you see a big opportunity, not just for typical JPEG MPEG compression, but compressing, like this graph problem we're talking about. We took an entire billion vertex graph, and each vertex is just a bit. So the entire cache of few megabytes, tens of megabytes, only holding a bit, one vector, one adjacency vector. So those kind of compact data structures is how you get a huge cache locality. Otherwise, the entire thing will be missing all the time. So it's parallel and distributed decomposition, and doing it efficiently is where I think real efficiency opportunity lies of 100x or more. So now my time is up. So I'll just do the part which I'm not very good at doing anyway, which is our product pitch. So we do have, so all designed this way. And so the very first thing we're doing is we're building a product line primarily for such applications where key trade-offs have been made to increase compute density, to improve bandwidth efficiency by offering scatter gather, by building and trading off single core performance with a more parallel core. And there's no free lunch. You have to make a fundamental trade-off which has not been made for a long time. We're slowing down the AMDAL, scalar part of AMDAL, by offering even higher parallelism. That AMDAL doesn't normally couple them. When you couple them, you get an optimization problem. So you would not necessarily see a speed up unless you have enough parallelism. And this is this line of many integrated core, which I was with our senior VP Kirk Skaugen at Supercomputing this past summer, and where I co-launched this with him. And this is our new product roadmap, which basically offers, like I said, a higher compute density platform for such emerging applications with large amount of parallelism, and with this challenge where you really have to trade off your compute for single thread compute for more parallel compute, right? And then you get terabytes per second, but the terabyte per second is on the on-die ring, and that's where it'll be easier to get byte per flop, not on external memory subsystem. So this software development platform is available now. It was available this summer, and the first product will be available second half of coming year, 2012. And as you can see, our goal here is, at least the numbers we are seeing, you see the trend that you've been seeing for multi-core gets significantly boosted for this class of problem only. It's not going to happen unless if you don't have enough parallelism, but you see a very significant boost in performance for all those traditional impact type applications. Now, whether this is enough to meet the exascale target, time will tell, but I'm personally very optimistic that this will. So this whole Knight's roadmap from Knight's Ferry to Knight's Corner and well beyond into exascale time frame is our new family of products. An important thing here is that it's the same architecture, the same 4 attributes: cache, core, thread, SIMD, same x86. So your entire tool chain just ports. No need to learn radical architecture, radical language. It's an attempt to see how far we can go through our traditional approach, where for whatever reason enough has been invested, and people want the code to run fast, but they also want to code fast. So that's really the thinking behind this, and to be able to support this kind of heterogeneity, which is not an architectural heterogeneity, but a performance heterogeneity through a same tool chain and all of our tool chain. So this is basically my summary. As you can see, this is an unfair presentation. Second half got 2 minutes, and first half got 25 minutes. And it also kept the content simple, and the real reason was that Intel legal and marketing left me alone with content which is not saying anything. And it's, yes, energy efficiency, I think applications understanding will play the most crucial role in getting the efficiency up. The huge opportunity lies in how a big impedance mismatch is there today in the core of computing that happens and the core of computing that's getting built. The algorithmic core is in a disconnect from the computing core that's getting built. parallel stuff from anywhere, CPU, GPU. That disconnect is where a big source of efficiency opportunity. Plus, looking at the problems differently in the massive data world we live in, I think, especially if we can understand how to decompose them right to make use of the iPhones that people are holding, is a huge opportunity for filtering data right there before you take it all the way to data center. And that's where the efficiency opportunity lies, much more than getting efficiency out of right at the data center. A lot of bad things have happened when junk photos got uploaded right there. So that distributing and decomposing the problem and doing something right there in the camera itself is a better way of solving problem in my view. And I think there's increasing trend in how more and more such things are happening in a more distributed decomposition problem. And computing density and locality awareness are still the key. Thank you.